I put up on the screen 4 data sets that have been plotted, and in each of these cases, believe it or not, all 4 of them have the same correlation coefficient. Okay, they all have the same correlation coefficient of so all 4 graphs here have the same correlation value. Okay, but you know, correlation, the interpretation for correlation, so R is equal to 0.817 for all 4, but the interpretation of, you know, positive trend with, you know, less scatter, you know, 0.8 is pretty, I would say, is closer to 1, and so that would indicate kind of a stronger relationship, less scatter. Positive trend, strong relationship, less scatter. That interpretation only works for this first graph. Okay? Because this one, so here R is also equal to 0.817, but the interpretation doesn't really work. Okay? It's not, correlation is not appropriate. And it's not appropriate because the data are very clearly not in a straight line. Okay. Over here, the data look like they're almost in a perfect straight line, with the exception of you got one outlier here, right? Otherwise, you would have a perfectly straight line right here, okay? Okay, and so if you have a situation like this, you know, you should plot it, okay, and then R equal to 0.817, also not a good interpretation, not a good representation of our data here, because we wouldn't, you know, if we took it like this and we assumed the data are, you know, have a little bit of scatter, that would be wrong. There's hardly any scatter with the exception of one outlier. And probably, I would expect this was probably a clerical error. Like the person typed the number in wrong, and that's why it ended up there. Okay? Or you should at least investigate this outlier. Why is this data point so far off from everything else? Okay? Ask why. Investigate the outlier. Okay. And over here, again, the idea is here we've gathered all of our data for x comes from when x is equal to 8. Okay. All our data is for x equal to 8, except for one point. Okay? So this would be kind of like, oh, is there an association between, I don't know, the number of hearts you have and how much money you make, okay? So pretty much everybody in the world has one heart. But let's say for some reason somebody is born and he has 3 hearts, okay? And let's say because he has 3 hearts, it made him very famous, and he's got all these deals, and so he makes a lot of money, right, compared to everybody else. Would it then be safe to say, well, oh, that means that the more hearts you have, the more money you're going to make? No, that would be silly, okay? It'd be silly to try to say that there's some kind of relationship there. So, and that's basically what we have going on here. We've gathered all data for when x equals 8, and then we have one data point way out here, and this is pretty much establishing our entire trend, because this one is higher than everything else, and large X seems to go with large Y. That's establishing the entire trend. But who knows? What if we gathered another data point at 19 and it's way down here? Okay, then everything falls apart. Okay, so you can't use just one data point out here to establish an entire trend. Okay. It would be as if, let's say, there's some country, okay, and you've only met one person from that country, and that person was a jerk. Would it then be fair to say, oh, everybody from that country is a jerk? I'm never going to go to that place? No, okay? You can't base an entire trend based on one observation, okay? And that's why it's important when you go traveling to be nice to everybody you meet, so they don't get the wrong impression about the country you represent. So, because people sometimes do that. They say, oh, I sat next to this one guy on an airplane and he was terrible, and he was from here. As humans, we tend to do stuff like that, but maybe we shouldn't. Okay, so all of this stuff with correlation is great, and the application of it is called regression. And specifically, we are learning something called linear regression. And the idea behind linear regression is that we want to create an equation for a straight line that we can use as a, to model the trend between x and y. Okay, so we want to model the overall trend between x and y. Okay, so we want the equation of a straight line that can be representative of the trend. Okay, so for example, let's say we have data points that look like this. Okay, we want to create, an equation for a straight line, maybe like this. Okay, just pretend this line is straight. And so this line is not perfect because it doesn't predict all of the dots perfectly, right? The dots aren't exactly on this line, but this red line does kind of a fairly good job of summarizing or characterizing the relationship between x and y. Okay? This line does not predict every point perfectly, Okay, it may not even predict a single point perfectly. Okay. Okay, but it's a good overall picture of the relationship between x and y. Okay, so when we write the equation of a line, the equation of the line will be in the form y equals a plus b x, okay, so or b times x. And actually I'm going to put a little, this is called a hat. It looks like a roof over y. It's called y hat. Y hat is equal to a plus bx. And what this means, so a is our intercept, and b is the slope. And so with linear regression, we are always trying to make a prediction for y based on x. Okay, so in the beginning you have to assign your variables to x and y. Okay, and you want to say, am I trying to predict this variable or am I trying to predict this variable? The one that you're trying to predict you assign to y. The one that you are using to make the prediction you call x. Okay? I'm going to go to the next slide here. Okay, so in regression, we are trying to predict one variable based on the other. Okay, the one being predicted, okay, the variable we predict is called y. Okay, other names include the dependent variable, the response variable, and the predicted variable. And the variable used to make the prediction is x. Okay, and other names independent variable, explanatory variable, and the predictor. Okay, and so you can take the same data set and you can choose to call this variable x and this variable y, and you can also switch them around and call this variable x and this variable y. Okay, so you can switch them around, but the one that you are predicting is y, the one you are using to predict is x. So let's try one out here. Okay. Okay, and so here, can I go to the next slide? No. Okay, so again, our regression equation is always in the form y hat equals a plus bx. Something happened. Okay, well, I guess that broke. So y is the variable being predicted, x is our predictor. Okay, so let's put this in the context of a problem. Okay, here we're going to look at a bunch of books. Okay, so we will look at many books. Okay, and what we're going to do is we will count how many pages are in the book, and we measure how thick the book is. We count the number of pages, and so this is one variable, and we measure the thickness of the book. Okay, so we've got two variables, and I'm going to just call this pages and thickness. All right, so we have two variables. Pages, thickness. Okay, and so from this data we can set up two ways to predict two regression equations. Okay, in one of them essentially we can play a game, right? A guessing game. And I can say, in one game I'm going to tell you how many pages are in the book. So this book has, I don't know, let's say 780 pages. Okay, this book has 780 pages. And I ask you, based on that, how thick is the book? Okay. The other game we can play is, I grab another book, and I say, oh, here's another book. I measure how thick it is. Oh, it's 2.6 centimeters thick. How many pages do you think it has? Okay, so we can play two different games here, right? And in each of those setups, we're going to have a different x and a different y variable. Okay, so in one game, we're going to say the book has 760 pages. How thick is it? Okay, and then the other game, we're going to say the book is 2.6 centimeters thick. How many pages do you think it has? How thick is it? It should be how thick do you predict it to be? Okay, so how many pages do you think it has? And I should say, how thick do you think it is? just to indicate that it's a prediction game. Okay, how thick do you think it is? Is that okay? All right, so in this case, what is our x? So if we're playing, the book has 760 pages, how thick do you think it is? X would be which variable?
760.
Not 760, that's the number. X is the variable pages. Okay, X is the variable pages, and Y, the variable that we're predicting, is what? Thickness. Okay, and over here we have X and we have Y. X would be what? The thickness. The book is 2.6 centimeters thick, so we're using that. We're using the thickness of the book to predict what? Number of pages. Is that okay? So you always want to make sure you are setting up your regression equation correctly, and you understand what is being predicted and what is being entered. Okay, so here we are using the number of pages to predict how thick it is. Over here we're using the thickness to predict the number of pages that we have. Okay, so it all depends on how you want to, how the questions are set up and how you're going to use the data. Okay, so let's try this out. Okay. And we're going to say, oh, it's going to be in millimeters here. Okay, so actually I'm going to go to the next slide. Okay, so we're going to do this. Okay, so we'll say Y is thickness of book measured in millimeters, and X will be the pages in the book. Okay, and we enter this into a computer. Okay, so we enter our data into a computer or a calculator. So the truth is you could calculate all of these things by hand, but I'm just gonna, but nobody really does it by hand. Okay, so we're just gonna say the computer spits this out. Okay, we enter our data into a computer and it spits out this. It spits out thickness, predicted thickness is equal to 6.22 plus 0.0366 pages. Okay, so based on this equation, all right, so I'll say based on the equation, how thick do we predict a book will be if it has 250 pages. Okay, so if a book has 250 pages, how thick do you think it'll be? So what do we do? We're going to use our prediction line. Okay, So here we're going to say pages, the variable pages is equal to what? 250. And we're going to plug that into our prediction line. Predicted width is equal to 6.22 plus 0.0366 times 250. Okay, so let's try this. So I do 6.22 plus 0.0366 times 250, 15.37. I get predicted width equal to 15.37. Okay? Or another way I can write this is width with a hat is 15.37. So what do I write? I say if a book has 250 pages in it, okay, based on my equation, or based on the regression line, I predict the book will be 15.37 millimeters thick. Does that make sense? Yes? No? Does this mean the book, so somebody goes, you go to the store and you find a book with 250 pages in it, okay? If you take it home and you measure how thick it is, how thick is it going to be?
15 millimeters.
So it may or may not be 15.37 millimeters. It probably won't be exactly that, okay? You take it home and you measure it, it might be 17 millimeters thick. It might be 12 millimeters thick, okay? This is just saying we are predicting that it's going to be this thick, okay? It doesn't necessarily mean that this is exactly how much it's going to be, right? For example, if let's say you go to a car dealership, right? You're thinking of buying a car. Maybe the sticker tag is $25,000, okay? How much will someone actually pay to get the car? It might not be exactly $25,000, okay? So, and maybe somebody else says, oh, I'm interested in buying this car, and this car's sticker price is $60,000. How much will that person pay when they to get the car? It may not be exactly that, okay? But it might be a good prediction, yes?
And also because, like, for indices, things doesn't take account of, like, the specific how big the individual pages are.
Yeah, this thing is just a prediction. There's all sorts of things that determine how thick a book is, okay? Actually, not very many things, okay? There's a few things, right? How thick the covers are, that goes into how thick a book is. How many pages the book has, and how thick the individual pages are. Those all go into determining how thick a book is. Now, if you knew all of those things, you can get a very accurate picture of how thick the book's going to be. But if you only know one of those things, just how many pages, you can still make a pretty good prediction, right? If somebody says, I've got a book and it's got 900 pages in it, you're not going to think that's going to be any, and somebody else says, I have a book and it's got 100 pages in it, you're not going to take any bets where you're going to say, oh, the 100-page book is going to be thicker than the 900-page book, okay? It might not fit this regression equation perfectly, but in almost all circumstances, that 900-page book is going to be thicker than the 100-page book, okay? Yes?
So there
The regression line is something that's given.
Yeah. We could spend a lot of time going into the nitty-gritty of getting the regression line ourselves, but in our class, I'm more concerned about you understanding how a regression line is used, okay? And so in the problems I will give you, the regression line will be provided to you, okay? There might be like 1 or 2 exercises in the homework where it says plug some numbers into this equation to get the regression line, but by and large, we don't really do regression lines by hand. We ask the computer to spit it out, okay? And so let's try an example here. Let me see. So for example, a computer might spit out something like this, okay? So this will be computer output. And it will say something like this. Dependent variable foot length, independent variable hand length, and it says foot length is equal to 15.8076 plus 0.5626 hand length sample size 17 correlation 0.404 r squared 0.1632, something like this. Okay, so a computer might spit this out. So based on what you see here, what's going on? I'll let you guys finish writing all of this down. What are we trying to predict? What are we using to make that prediction? What are we trying to predict?
Foot.
The length of a foot, okay? Someone's foot length. So what we've done is we've interviewed how many people? 17 people. And we asked them, how long is your hand? Okay, so somehow we've defined how to measure hand length. We asked them, how long is your hand? And then we also measured, how long is your foot? Okay? And what kind of trend do you think we're going to see?
Bigger hand, positive trend.
Positive trend, right? People with big hands will probably have big feet. People with small hands probably will have smaller feet, right? Generally, that's going to be the trend, right? Just even thinking across men and women, men tend to have larger hands than women, tend to have larger feet than women, okay? And by and large, you know, I imagine LeBron James has big hands and he probably has big feet, okay? So anyway, so that's what we're doing. We're trying to predict how long someone's foot is based on how long their hand is, okay? And we get 17 data points to create our equation, and then we can say, okay, well, if I take someone else and we measure their hand length, then we can make a prediction for foot length. Okay, so using this, let's say someone has I have no idea what coefficients are being I have no idea if these are being measured in inches or feet or centimeters. In centimeters, everything's in centimeters. Okay, so let's say someone has a hand that is 18 centimeters long. Okay. What do you predict what do you predict to be the length of this person's foot? Okay, so go ahead and take, we'll say, 30 seconds to answer this question.
9.
Yeah, 25.9 something, right?
Yeah.
So what we want to do here is we're going to say foot length is equal to 15.8076 plus 0.56266 times 18, right? So I punch that in, 15.8076 plus 0.56266 times 18, and I get 25.93 something something something. So this is how long we predict the person's foot to be. Okay? Let's say we actually measure the person's foot. Okay? Actual foot length was 30.2 centimeters long. Okay? So I'm going to ask another question. How far off was our prediction? Okay. And how far off was our prediction? This is known as our residual. Okay. Okay, the residual is always the difference between the actual value minus the predicted value. So someone with an 18 centimeter hand actually had a foot that was 30.2 centimeters. So how far off was our prediction? Yes. Yeah, so we do 30.2 minus 25.93, and we get 4.265, okay? So our residual is equal to 30.2 centimeters, or I'm just going to write 30.2 minus 25.935, and we get 4.265 centimeters, okay? So our residual is 4.265 centimeters, or this is how far off our prediction was. Okay? All right, let's just do a quick check of our understanding. What is our x variable? What is it?
Dependent.
Okay, what, in the context of our problem, what's the x variable? Yeah. Hand length. Hand length is our x variable. Okay, so that should make what our y variable. What's our y variable? Foot length. Okay. What is the value of r?
0.404.
Is our correlation value 0.404. So what does that tell us about the relationship between hand length and foot length? What's that? Yeah, so there's a positive trend, but it's not very strong, right? So knowing how big someone's hand is tells you a little bit about their foot, but not a whole lot, okay? Overall, people with big hands tend to have big feet, but in terms of getting an actual prediction, you might be off by a little bit. Okay. So that's what we have there. Is that okay? I want to break down each thing, okay? What did I say this is called? This value? This is known as the, not the x, the hand length is x. This is our slope. And what is this? This is our intercept, right? I'm hoping these terms are familiar to you from like your algebra days, slope and intercept. Okay, so that's actually worth noting here. So if I were to ask you what is the slope, you would tell me the slope is equal to 0.56266, and the intercept is equal to 15.8076. Okay? Let's talk about what the slope and the intercept mean. Okay, so we're going to keep, let's say we keep this. Okay, on to our next slide. Okay, so you tell me, I'm going to say make predictions. So someone has make predictions for foot length for someone whose hand length is ... Okay, so make a prediction for foot length if the hand length is 16 centimeters, 17 centimeters, 18 centimeters. Okay, so this will be hand, and over here we have predicted foot length. Can we do this? Okay, so let's do this. All right, so I do 15.8076 plus 0.56266 times 16, and I get 24.81016, and then and let's go back up. Whoops. And I'm going to just change this to a 17, and I get 25.37282. And I go back and I change this to an 18, and I get 25.93548. Can we see that? Okay, so here's a question. How much did this go up by? To go from 16 to centimeters, how much was the change? Well, I can do this. I can do 25.37282 minus 24.81016. And what do I have? I see that to go from here to here, I just added 0.56266. Can you guys see that? Okay, what about to go from here to here? Same thing, right? I can do the subtraction, 25.93548 minus 25.37282. So I can do this thing minus this thing, And what do I get? I get the same thing. So to go from there to there, I would get 0.56266. Is that okay with everyone? Yeah? Okay, so if I put in 19 centimeters, what would I predict over here? Instead of using the full equation, I can just say, what? I'm going to do 25.93548, and what would I add to that? 0 plus, 0.56266, right? And so if I can just add plus this, and I would get my prediction, 26.49814. Okay? And so what is that number that I keep adding? That is my slope. Okay? So the slope, and this is important, okay? The definition or the interpretation of the slope. Okay? It is how much our prediction changes. If we add 1 to x. So if I add 1 to x, how much does my prediction for y change? It goes up by the amount of the slope. Okay? So in the context of our problem, I can say, so this is also important, if we increase hand length by 1, or if we add 1 to the hand length, by 1 centimeter, my prediction for foot length goes up by 0.56266 centimeters. Okay. So that is the interpretation of the slope. Just want you guys to read that over, make sure it makes sense in your brain here.
What's the difference between slope and, in the previous chapter, the deviation, standard deviation?
So the standard deviation is a measure of spread. Okay, it's for one numeric variable, and it just tells you how much the numbers are spread out. Okay, this is for regression. We have two variables. In our case, it's the hand length and the foot length, and we're trying to see if there's a relationship between those two variables.
Can't you say the slope is the deviation between the y?
The slope is not the deviation, okay? The standard deviation is a measure of spread. It tells us if the numbers are all very different or if their numbers are all together. The slope does not tell us that. The slope does not tell us if foot length, there's a wide spread in foot length, or there's not a lot of spread in foot length. It doesn't tell us if there's a lot of spread in hand length or not a lot of hand. It just tells us how foot length is related to hand length. If hand length changes by 1 centimeter, how much does foot length change by? That's what this slope tells you. It doesn't tell us much else. Okay, that's the only thing it tells us. Is this okay? Yes.
Can we make predictions by just graphing?
Hmm?
Can we make predictions by graphing?
You can make predictions by graphing, but you're not going to have as much precision there. Okay? So that is the slope. Let's just flip back a couple pages here. Okay, so over here, my slope is what? What's the...
0.036.
0.0366. This is my slope. And this is thickness in centimeters. So let's just, I'm going to just tag on interpretation of the slope here. Okay, so my slope is 0.0366. Okay, what is the interpretation of the slope here? It means if I increase x by 1, my prediction for y changes by the slope. So what does it mean to increase x by 1 here?
Increase the amount of centimeters.
Not the amount of centimeters. What is my x?
Pages? Yeah.
Pages in the book, okay? So if I increase the number of pages in the book by 1, basically I'm adding 1 page to the book, my prediction for how thick the book goes up by what? By 0.0366, okay? So basically every time I'm adding a page, I'm predicting the book is getting thicker by 0.0366 millimeters, okay? So 1 page, it's not going to make a bunch of difference. But if I add 100 pages, then it'll increase the thickness of my book by what? 3.66 millimeters. If I add 1,000 pages to the book, it'd increase the thickness of the book by 36.6 millimeters. Does that kind of make sense? So that's what we've got going on here. Okay? If I add 1 page to the book, my prediction for the thickness goes up 0.0366 millimeters. Okay, so it's very important what we keep in mind what x represents. X is not the hand length, or the, in this case, it's the number of pages in the book. So to add 1 to x means the number of pages goes up by 1. Okay. All right, so let's we'll keep trying here. Let's talk about the intercept. Okay, so the intercept here is 15.8076. This is the intercept. The intercept is the prediction for y if x can be equal to 0. Okay? X cannot always be equal to 0. Or it might not make sense to have x equal to 0. Okay, but if x can be equal to 0, that's what we would predict y to be. Okay. So, in our case, what would it mean to have x equal to 0?
Person has no hands.
Yeah, it means the length of the person's hand is 0 centimeters, okay? So either it means they have no hand or something. It doesn't quite make sense. Now, there are people who are born without hands, but we would not then use that fact to predict how long their feet are, okay? Okay, so in this case, there will be people who don't have hands, okay? But it doesn't make sense to use that information to predict the length of a foot, okay? So in our context, you know, the direct interpretation of the slope would be if someone had x equal to 0, we predict their foot length to be 15.8076. But that interpretation does not make sense. Okay? So in this case, the interpretation of the slope, I'm sorry, not slope, interpretation of the intercept does not make sense, okay? The direct interpretation would be something like, if someone has a hand length of 0, we predict his or her feet to have a length of 15.8076 centimeters. Okay? And it doesn't make sense to use this information to make a prediction. On the other hand, if we had a situation where predict the cost of the Honda based on its mileage, can you have a car with 0 miles on it? Yes, that would be a brand new car. And would it make sense to try to predict the value based on that information? Yes. Okay? So trying to, if we want to predict the value of a car based on its mileage, the intercept would be your prediction for the value of the car if it were brand new, if it had 0 miles on it. That would be the interpretation of the intercept. Does that make sense? Good for everybody? Okay, we'll end here tonight. You got some homework from chapter 4. You're gonna have to do maybe a little bit of the reading to make sure to fill in any gaps in your knowledge that I might not have covered everything. We've got a quiz next week, so we'll see you then. We have a question. Oh shoot! Okay, before you guys leave, sorry. Thank you. Please sign your name next to sign in next to your name. Sorry. Thank you for that reminder.